Sorry, too bad. I personally would start at the hex. I already started coloring in some other stuff because I looked at somebody else's answer and found their mistake. So I would start at the hex, and I would just draw out a hex, which I happen to know is 1, 2, 3, 4, 5, 6 carbons. Okay. The next part is I would focus at the core or the root or the highest functional group. It ends with ic acid or oic acid. I may have screwed that up, but let's just say I was right. Which means I have a carboxylic acid. Carboxylic acids, by definition, are at position 1. So I'm going to read this left to right, position 1. Okay. If this is an ACS test, it might not actually be a bad idea if you weren't looking at the multiple choice, if you're just going to draw it out, to actually draw the carboxylic acid at the other position. Why?
Because you don't know which place you're starting at?
Yes, but remember the ACS is going to try and convolute the question so it isn't quite as straightforward as just reading the answer off. And if you looked at your answers and started with position 1 left to right, well, that's how most people write. By just switching the numerical order, it can make the right answer look wrong. So if you're going to just try and draw out the structure before looking at answers, you might actually start numbering the opposite direction because you might kind of accidentally draw the answer as they've got it drawn. Kind of make sense? So we're thinking about the tricks and how we could make it more difficult on a multiple choice test. Okay? The next part is really easy to miss. If the carboxylic acid is by definition at position 1, why am I saying position 2? It says 2-ene oic acid. The oic acid is the carboxylic acid. The ene means there's an alkene. So there's a double bond. That double bond starts at position 2 and by definition will continue further down the chain. So it'll run from position 2 to position 3. Okay. After that, I've got the oxo at position 4. Well, what did oxo mean? Okay. We could jump with OH. What does hydroxy mean? If it means the same thing, why would we use 2 different words?
Because you can't say hydroxy has its word.
No, you can. That's actually perfectly valid, unfortunately. Okay. The oxo isn't a hydroxy. Okay. At best, oxygen, so that's good. And at the 4 position, so if we count that at 1, 2, 3, 4, I know I have an oxygen there. Okay. It can't be a hydroxy. Okay. I'm not suggesting any other carbon groups because it's just oxo. There's no meth, eth, pro, bute, pent, any of that. So what would that then be? It's a carbonyl. The oxo is actually referenced to the carbonyl. For those of you saying ketone, that is the correct functional group here, but oxo can also apply to aldehydes. Okay? It's really just saying the carbonyl. Okay? What's that? How would we know that that 4-oxo was actually an aldehyde and not a ketone? If it's at the end of the structure, that's the only way you would know. So if we got rid of 2 carbons, so we get rid of the 6-hydroxy and we make that 1, 2, 4, 4 bute. Okay, so if we had 4-oxo bute 2-ene oic acid, then that would become an aldehyde. Okay, because there aren't any other carbons connected afterwards. Okay. The next part is the hydroxy at position 6. 1, 2, 3, 4, 5, 6. We have a hydroxy, which is an OH. And we now have our structure. Is there anything in that structure that jumps out that you're like, but what about this? Is that double bond a cis-trans option?
No.
Okay. If you're saying no, then I cannot identify this as a trans double bond or a cis double bond. Is that true? Okay. For reference, if we went back a couple slides, what we would need to do, I need to clean up some of that space down there. For deciding cis and trans, cut the double bond perpendicular to the bond axis, and then look at half of it. So I'm going to look at the right lower half. Hydrogen versus carbon. Is there a difference in priority? Yes. Which one's higher priority? The carbon. So I'm going to star the carbon. I'm going to look at now the upper left half. It's, hydrogen versus carbon. Is there a difference in priority? Yes. So I'm going to star that carbon. Now if I cut parallel to the bond axis, are those stars on the same side or opposite side, or can I not tell? Opposite sides, which means this structure as drawn is trans. Do I need to worry about it as the question is asked? No. Why? It should have said at the beginning 2E. 2E. Okay? Because that's not there, we don't have to stress about it. I don't know. The other one that I think is a lot more appropriate, cis is on the same side. Everybody laughs at me. I didn't come up with it. Okay? Does that kind of work for our nomenclature? Questions about what we got there? Okay. One thing I did throw in while you guys were working on it, exam 1 functional groups. Alkanes, alkenes, alkynes, alcohols, aldehydes, and ketones. Okay? All of those functional groups are fair game. I won't be throwing on the acids or the esters or the amines. Why not? We don't really see those. We might see the amine show up in this unit, but we don't really see those this unit. The aldehydes and ketones are kind of borderline. Yes? Why did I not draw it cis? Could I have drawn it cis? Yes. Does the question ask me to specify cis or trans?
No, but why didn't you?
So what if I had drawn it cis? What would it have looked like?
We went through this whole thing,
Yeah.
and then
Why did I not draw it cis? It would have looked weird. That's it. That's the only reason I didn't draw it cis.
Can you show it?
but you know, but see, when I
Horrible people. You're going to make me draw it? You drew it cis?
I did, but that
Wow.
one's drawn cis up on the top left, and it doesn't look weird on my paper. I'm having a bad day, just don't.
Okay. Let me draw it up. It's hard. I can't even draw. 1, 2, 3. 1, 2, 3. Yeah, that's what I said. They didn't want to draw it. Oh, so, okay. That would be the cis.
Is that
Right.
Oh, that's not.
That, well, it matches the name. It matches the name because the name did not specify cis or
If it
trans.
did specify, that's what you have to do for cis.
This is what you would have to do for cis. Right? The reason why I wouldn't have drawn it that way is I start with the hex, I get my 6 carbons out. When you draw out 6 carbons, how do you typically draw them?
A chain.
As a zigzag chain, which is by definition setting it up as trans. Okay? So the only way you would know to do cis is if you actually started, saw that it was cis, drew the double bond, and then drew from there. I think that's too difficult because I'm now not starting with the root of the structure, I'm starting with the middle of the structure. Okay? You, on the other hand, didn't think it was that difficult, so you did it that way. Right? Different opinions. Your drawing is probably just nicer than mine. Okay? We good with that? Yeah.
For the exam 1 functional groups, is that just for nomenclature?
Just nomenclature, yep. And then functional groups is too hard to classify because we'll see a bunch of functional groups show up because we're looking at mechanism, not function. Okay? So, when we're looking at our addition reaction with electrophiles, so what we've already talked about with our addition reactions is when the pi bond, our nonpolar pi bond, was acting as a base. So it was reacting with a strong acid, and it needed to be a strong acid. Why did it have to be a strong acid? What's that? The acid would dissociate, true, but how does that have anything to do with the reactivity of the addition reaction?
Has to accept something.
What has to accept? Yes. Our base, the nonpolar pi bond, has to share electrons with a hydrogen. Right? Why do I need a strong acid? Why can't I use a weak acid with a nonpolar pi bond?
Because it wouldn't be able to give away its hydrogen.
The nonpolar pi bond, the electrons aren't polarized enough to react with a weak acid. Okay, so I need a strong acid to polarize that bond enough to actually cause it to react. Alkenes on their own aren't particularly reactive. We need active acids or active electrophiles, okay, to force them to react. Right? When we go through and look at our addition reactions, almost all of them involve some kind of cyclic structure, either as an intermediate or as a product, okay, or as a transition state. And that has to do with kind of the reactivity of the alkene. Okay? So what I went through and did in that video that you all watched is tried to come up with ways to group reagents into categories that I could then memorize what's happening within the category, and the reagents just fit there, as opposed to having to memorize all of the reagents and all of their apparently distinct results. Okay? So when we go through and look at chapter 12 is primarily this tri-intermediate. Okay? So three things, a three-center intermediate. Okay? We see that with elemental bromine. We see that with MCPBA. We see it with diazomethane, and we also see it with the mercury reagent. Okay? There are also tetra-intermediates, where there's 4 centers. Okay? Those 4 centers also show up in chapter 12 with the boron reagent. Okay? After that, we can jump up to 5 centers or 6 centers. That gets up into chapter 24. Okay? What we're evaluating then is looking at those other reagents. So how can we make sense of these so that we don't have to memorize each as its own unique thing, but how can we group them to organize them, okay, or to come up with patterns? That patterning is what I came up with on that kind of summary. When we go through and look at our pi bonds acting as nucleophiles, they have to react with an electrophilic species, which will typically be our Lewis acid. Right? And when I went through and evaluated those, I tried to come up with patterns. And what I noticed is that if the Lewis acid is also a nucleophile, I end up with 3-membered transition states or intermediates. If when I ran that reaction, because our Lewis acid has to be connected to some kind of leaving group, if that leaving group is now really, really, really tiny, okay, I end up with 4-member transition states or larger. Why would I end up with a larger transition state if the leaving group is tiny? If the leaving group is tiny, can it leave? No. So the only way it can leave is if we end up with a simultaneous reaction. It immediately attaches to the alkene at the same time that the alkene attaches to the Lewis acid. So we never actually have a traditional leaving group because it never leaves any structure. It just exchanges which structure it's on. Right? If my Lewis acid is a nucleophile, when the pi bond reacts, the Lewis acid then has what? Electrons, because it's a nucleophile, and can immediately react back with the alkene. Well, how? What? Why could it react with the alkene? Draw a resonance structure for the alkene that I've got set up here. As a hint, there's 2 of them that you could potentially draw. Doesn't really matter which one. Right. One I would draw is taking the electrons, I'm going to put them there, which means I'd have a negative here and a positive here. Right. We may not like that resonance structure. Why do we not like that resonance structure? It's charged. But what is nice about having a charged structure? I can see where it's reactive. So the neutral structure is always what we have to draw and present to everybody else, much like science. When I go through and do a science experiment, it's going to suck. And that's not just because it's me. That's because anybody doing a science experiment is going to suck at it, okay? Particularly the first time, probably even the first 5 or 6 times. After that, we've picked up a pattern on how the reaction works. We've controlled the variables. And we end up with maybe 5 or 6 repeatable, awesome experiments. I didn't go out to publish that to the world. Do I show the world my first 5 or 6 horrible attempts? No. The only thing I want to show the world is where I did great. So the world thinks I'm insanely smart and brilliant. And instead, I'm probably just a mediocre moron that got lucky. Right? That is scientists. Right? But I'm not sure if I'm allowed to group myself as a scientist, but as a whole, scientists are very non-confident. I'm sure there's a better word than that. And so they need something to inflate their ego. What is that ego inflation? We hide all our failures and we only show people how good we were. Right? Which means you guys come in and you see scientists and think, wow, they must be really brilliant. No, they were just an idiot that kept trying it. Right? Like the guy testing his ability to walk through walls. You didn't hear about that? He just kept walking at a wall through his whole life. Eventually he made it through the wall because he broke the wall. Okay? But he made it through and everyone's like, oh, that was amazing, you made it through the wall. No, you were just an idiot that was persevering and eventually broke the wall with your forehead. Right? That's scientists. Okay? Those are being like, really? Yes. Okay? So, why draw the resonance structure? What is reactive in the alkene? The positive or the negative? The negative. Why am I saying it's the negative and not the positive? I'm evaluating the starting structure. The starting structure is the pi electrons. That's what's making it reactive. So even when I go up to the resonance structure, I'm still holding my starting pi structure or my starting neutral structure as the source for my knowledge. So those electrons then do what? Well, they come out and they share with a Lewis acid. Okay? What happens if that Lewis acid is a nucleophile? What does it also have? Electrons. Okay? Well, if the pi bond came out and shared its electrons with the Lewis acid, what is by definition then also formed? Fair enough. A bond between the carbon and the Lewis acid and a carbocation. What do carbocations want? Electrons. What does my Lewis acid have? Electrons. They can immediately share back, and I form a cyclic intermediate, that 3-membered transition state. The classic example for this is if I react my alkene with Br2. Whoops. So if we draw that out, bromine, we draw on all our electrons. The first thing that tends to challenge students is we look at bromine and we think bromine will always act as a nucleophile. Why? Because when we think bromine, we think bromide, which is negatively charged. Is bromine negatively charged? No. Bromine is actually neutral. Okay? If I bring electrons near it, what happens? I can polarize it. I eject the leaving group. Is the leaving group tiny? Bromine is one of our larger elements. No, bromine is very, very large. Add to that, the initial bromide that was attacked has what? Electrons. So what happens? I kick out the leaving group and I get the simultaneous attack back, and the result would be everybody's favorite structure. Why? Some people laughed, so you at least know why. Or maybe you just laughed because you thought it was funny. Why would everybody go like, yay, that's the coolest structure ever. I love that structure. Okay, fair enough. We had a lab on it. It was kind of sarcasm. It's usually not people's favorite structure. Why might you not like this structure? Why is it really unstable? It's not a carbocation. It's a bromine cation. Carbo necessarily means carbon. Okay? But we're used to seeing only carbons with positives. Now we have a positive bromine. Should bromine ever be positive? No. So we don't like drawing it. Do we have evidence that the structure exists? Yes. Okay, and that comes from the mechanism, okay, or experimental evidence that's supporting this mechanism. Take a closer look at that structure for me. Is there anything special about that product? There are 2 chiral atoms there. Okay, which means, do I need to worry about showing chirality? Yes. Why do I need to worry about it? Does my starting material show some aspect of sort of stereochemistry? Is that a trans double bond? Yeah. How does this reaction work? 1 step, multiple steps. How many reaction arrows have we shown? 1, which means it happens all in 1 step, which means what happens to the orientation of those 2 groups? Stays the same. They have to be on opposite sides of the breaking pi bond, which means one is wedged and the other is dashed. Okay?
Why is BR positive?
The BR is positive because what happened to it? We lost electrons, so loss of electrons. Gain electrons. So if it lost and gained, what would its charge be? Neutral, because it started neutral. What else did it do?
Lost.
It also lost electrons there. So the net result is it comes out as a positive. Does bromine want to be positive? No, so what happens? It tries to steal electrons from one of those carbon atoms. Which carbon atom? It doesn't matter in this case. Why? They're identical. As it steals those electrons, we'd form a carbocation. We said there's no carbocation. So something has to help that bromine leave. Okay, what charge would build on that red carbon that's losing electrons? Positive. What do we need to find in solution? Not more bromine. Electrons. What was our leaving group? Bromide in this case. That bromide can now come in and attack, ejecting the first one, and we'd end up with our product.
How do the piles
What we'd have to do is, do we have 4 different things connected? CH3 versus hydrogen, are those different? Yeah, is hydrogen different from bromine? Yeah, is bromine different from that CH3?
Yeah.
Yeah, so there's 3. Where's the 4th?
It's the bond.
What is that? The purple arrow.
Carbon bonded to 2 carbons.
Yeah, so is it a CH3?
No.
Is it different from the CH3? Is it different from the hydrogen? Is it different from the bromine? Son of a bee, we got 4 different things. Both of them all have the same issue. They're both chiral atoms. Okay? And this is how excited I am about talking about chirality. I'm not going to show the wedges and dashes for that final product. Okay? One thing that I did show, though, where's the bromine? The bromine is coming in from the back side of that bromine leaving, which means the 2 bromines must be on opposite sides. The net result, so when we go through the mechanism, we can see all of those pieces. The net result, we would then talk beginning to end and say, well, what kind of a reaction happened? So number 1, what was the kind of reaction that happened? In addition, I added Br2 to an alkene. So it's an addition, 1 piece. What type of addition was it? Okay, electrophilic, good answer. Continue. I heard somebody else say it. And anti-addition. The bromines are added on opposite sides of that old pi bond. Okay? And that very first step, was it an anti-addition of the bromine? No, it was a syn addition. Okay, so depending on where you're classifying your anti and syns, you could end up with different explanations for it. So be careful. Typically, when we're referencing anti and syn addition, it's beginning to end, reactant to product. We typically do not reference the intermediates. Okay? Henry? Intermediate to product, yes, it's still one step. Because you open, well, you didn't really open a question there, but I came up with another question. What type of reaction or mechanism happened in that second step? Okay. We have a nucleophile adding to a carbon. What is leaving from that carbon? Electrons going to bromine. What could you tell me about bromine? A leaving group. I have a nucleophilic attack with a leaving group. I have a substitution. Is it SN1 or SN2? It is one step, which means it is SN2. The one had to do with the number of species involved in the rate limiting step. The two means all the species are in one step. So one step, two species. So that second step is technically an SN2. Didn't we say this was an addition reaction? Yeah. Does that mean each of the mechanistic steps must be additions? No. Okay. Mari first.
So you did the wedges and dashes for the final product with the top right CH3 dash and the bottom.
Yeah, as I said it, it's not that bad. Yeah. Okay. Just for throwing it out as an ACS question, if they ask this, do you think they would show it to you in this form? Nope, probably not, because that's a really straightforward, easy way to show it. What would they likely have done? Right, they could put the CH3s in the same plane. How? By doing a rotation about the sigma bond. That would make the answer look wrong because it looks like the CH3s would be on the same side of the equation or same side of the bond. But as long as you're maintaining the stereochemistry and just doing a rotation, you haven't changed the structure. Okay. What else could we do to make that really fun on an exam? Sorry? We could shift it to a Newman projection. Okay, for those of you making faces, be like, I really have to know all that. Yeah. Yeah, you do. Okay? This is where model kits can come in handy because you could draw the product, draw the model, quickly turn it into a Newman projection and be like, that's my answer. Okay? Questions? Oh, yeah. Yeah.
So the bromine that attacks that one,
Blue or black?
the blue one.
Okay.
That one, is it just some other random bromine? Or
So we got to be, and I'm going to be nasty and nitpicky. I apologize. It's not bromine. What is it? Bromide. Okay. And it's not just some random bromide floating around. Where did that bromide come from?
From the leaving group?
From the leaving group of our initial bromine.
But if it left as a leaving group, why would it want to attack that?
So we're saying it left as a leaving group because it's stable on its own. That's fine. Okay? Something can be stable. Okay? Is my pen stable on this table? What'd you just say?
For now.
For now. What happened? Can I make it move? Can I make it unstable? Yes. How are we making that bromide unstable and reactive? Does bromine want to be positive? No. That's why that bromide is now forced to come back in and react, because something else in solution is more reactive, forcing the bromide to react.
So what makes it a leaving group?
Okay? What is a leaving group? For those of you just being like, I'm not going to answer that or help her out, feel free to jump in and be like, this is what a leaving group is. What is a leaving group?
Accepts negative charge.
Okay, it accepts electrons. Okay, so let's draw an example here. Would I expect hydrogen to be a leaving group? In my arrow pushing here, isn't that accepting electrons? What makes bromine a better, or bromide a better leaving group than hydrogen? Okay, it's not just that it accepts electrons, but why is it accepting electrons? Okay, we could evaluate charge, then size, then electronegativity, then resonance, and then inductive effects. All of those things come back to contribute. So why is bromide good? It's still charged, okay? So it should have the same leaving group ability as hydrogen, because they're both charged. What's the next thing I evaluate? Size. Is there a difference in size between bromine and hydrogen? Yep, bromine is massive, okay? One of the questions that does pop up every so often within that is, well, what is big enough? Okay.
Whatever's bigger than.
I asked the question, so you have to answer it. Not quite, but close.
It depends on like the situation.
Better?
Depends on what you're looking to.
Kind of. How do we determine what is large enough?
When it gets done.
When it happens. Okay? When I go into lab and I test it and it left, it was big enough. Okay? And we don't have a lot of good explanations for that in this class. Why? Because what is the official explanation? Quantum physics. Okay? Do you want to learn about quantum physics at the same time we're doing this?
Yes.
Okay? Some people, yes. Some people, no. It takes a course that is already jam-packed within a year and probably scales it out to 2 or 3 years. Okay? That's not reasonable to try and do. Okay? So if you're learning on your own and just having fun, you have no other kind of goals to get out of this class, you can talk to me about quantum physics. If you're trying to get out of this class and go somewhere else, don't worry about quantum physics. Okay? And what you end up having to do is memorize a little bit. Okay? Kind of, sort of? So let's throw in, erase all those. I sure hope you are okay with that. If you're not, sorry. Actually, I'm going to cheat. Get rid of all that. I'm going to draw it like so. What do you think? That reagent, H2CN2. Should that best match the top box or the bottom box? First thing, what is misleading about what I drew? I haven't shown any of the connectivity. So the first thing that you should go through when you draw this or try to evaluate this question would be draw the Lewis structure. And I think I did that right. We've got a Lewis structure. Remember the one I drew was neutral, but that one has charge. Charge is balance. It is overall neutral. Okay? How does that structure react?
Is the carbon-nitrogen bond break?
Why would the carbon-nitrogen bond break? So, I'm waiting for something to yell at. Or shout into the microphone. Why am I concerned about the carbon-nitrogen bond first and foremost? Positive charge in the nitrogen. Nitrogen is more electronegative than all of those atoms, and nitrogen does not want to be positively charged, so it needs to get electrons. If it took them from the nitrogen, that doesn't make sense because nitrogen is more electronegative than carbon. So those electrons are likely going to get pulled from the carbon. What does that then mean happens? Does the carbon become negative? Does the carbon become positive? No, this is an insanely tricky one. It's known as a carbene. Okay? It becomes neither positive nor negative. Why? It started negative, it lost electrons, which then means it's neutral. Okay? Why is the carbene an extra weird structure? It doesn't have its octet. So that carbon is now reactive because it doesn't have its octet. So what happens? It looks for electrons in, say, the pi bond of our alkene. So the electrons come out to stabilize that carbon. At the same time, what does the carbon have? Lone pair electrons, which means it's a nucleophile. Those electrons immediately come back and attack. The result being a what? Four-membered? A three-membered ring, because the nitrogens get ejected. Okay? Again, I'm getting lazy with how I'm showing that system. This is all happening at the same time, which means those two groups must maintain their relative position to each other, the methyl groups. Okay? That is bad mojo. I already just yelled at Colin earlier today. We aren't allowed to draw that because that structure three-dimensionally is horrible. Okay? So we aren't allowed to draw that. That methyl should actually be rotated and drawn down here to better represent three-dimensional structure. But if I do that, now it becomes misleading because the methyl groups look like they're on the same side. But according to my starting material, opposite sides. What does that mean? I need my wedges and dashes. Does this one continue to react?
I don't think so.
Why are you saying no? We have a full octet everywhere. If we looked at the bromine reaction before, when I formed that three-membered reaction, I still had an octet though.
But it was charged.
But it was charged. Is this one charged? No. Does this one continue to react? No, it stalls here. So by evaluating those charges and the structures along the way, we can start to come up with predictions about how these things might react without actually knowing the reagent. Okay? That's what I'm trying to get you to look for. A lot of that pattern recognition comes from practice. Okay? It wasn't till last fall when trying to go through this and being like, there's way too many different reactions here, there has to be a way to simplify this, that I even came up with this. That's after 10 years of staring at the same reactions. Okay? It is a long time. And I'm probably not done. Come back in 10 years and you'll probably see something entirely different. Okay, so what we're trying to do is come up with ways to get through this with memorizing minimally. We still have to memorize, but if we can come up with shortcuts to group these reactions, we can simplify our life. Yeah, Mo?
So is that stable?
Stable is always relative.
But doesn't it have like a lot of steric hindrance and stuff?
Not steric hindrance, not the right word. Strain.
Yeah.
Okay. Yes, there's lots of strain within the ring. Cyclopropanes on their own have a whole nother class that we could talk about for reactivity and stabilities. Okay. They are very unstable, but they are not as unstable as we might have predicted.
So even though it's kind of relatively unstable, it still won't react again?
Not easily. Okay. Nowhere near like the bromonium from the previous one. Okay. Kind of makes sense? You want to try another one?
Yes.
Cool. It was also kind of rhetorical because I was going to do it anyway.
Are we gonna talk about the phone number or?
What, I don't know. You answered. I asked my question first. Oh yeah. Lecture mic is in the house. What do you think's going to happen? There's no leaving group. What do you mean there's no leaving group? Can't the hydrogen just take electrons? Can't this just happen? Hydrogen is a horrible leaving group because It's tiny. It can't stabilize a negative charge. So I don't have a good leaving group. Okay? Do I have a nucleophile? Does the hydrogen that attacked have electrons?
It's a proton.
Okay? The hydrogen that's attacked here, at best, is a positive charge. The only electrons it had were in that bond. And where did I show those electrons go? To the other hydrogen. So does this fit in our Lewis acid as a nucleophile category? No. Where does it fit? Our leaving group is tiny. Okay? That leaving group is so tiny that it cannot eject from the molecule in and of itself. So what does that mean happens? It immediately comes back to the structure. So there's hydrogen number 1. Call it purple hydrogen. Where's hydrogen number 2? Well, somewhere near next to it. Bonded to the other carbon. What happened to the bond connecting the purple to the orange?
Still stays.
What happened to that bond? Where are those electrons now? The electrons went to the other carbon. Meaning, is there a bond between the hydrogens anymore? No. The electrons actually went with the orange one to form a bond to the other carbon. And we've now added those 2 hydrogens across that structure. Okay?
Can I ask a question?
Maybe.
It's serious.
Yeah.
Okay, so.
Oh, so I guess I should be serious. Yes.
There's wonders of BH3 PHF, that reaction began to
We'll talk about that too.
That's similar to this.
It is. It is very similar to it. Right? So this definitely doesn't fit under our Lewis acid as a nucleophile. It fits under our leaving group as tiny. What kind of addition did I do? That's not a good leaving group, right? So it can't leave and then come back on, which means the hydrogens are added at the same time, which means what type of addition did I do? A syn addition. Right? Which means what happens to the orientation of the methyl groups? They need to be locked in as they were at the starting, which means they would need to be on opposite sides. Dang it, do I need to show that here? When do I need to show wedges and dashes? When I have a chiral atom. Do I have a chiral atom? No. So I don't need to worry about that. Complications within this. The alkene, that nonpolar pi bond, is it reactive? Is it very reactive? No, it's nonpolar. How about that hydrogen? Not reactive. Why? Because hydrogen's a bad leaving group. Tiny. Neither of those structures are reactive. Should this reaction work? Nope. In fact, it doesn't. If I take hydrogen and I mix it with an alkene, nothing happens. But if I add a catalyst, like platinum, palladium, nickel, okay, poisoned, no, now it'll work. Okay? So I need something to help bring those 2 species together to actually force it to happen. By evaluating the chemistry of each of those pieces, I can come to the prediction that I need a catalyst to cause this to occur. Okay? It is that thought process I want you to be thinking about when you look at the reagents. Make sense? I'll take that as a yes. There was a suggestion for BH3. Actually, I'm going to ignore that. Almost always written as BH3.THF. Sometimes you'll see it as B2H6. Almost always you see THF written next to it. Not a big deal. Okay. What is happening with BH3? Again, we have the issue of it written out like a formula. So what should we do?
Draw the structure.
Draw the structure. So when we draw out the Lewis structure, what do we find? Because I don't want to draw it again.
Lone pair.
The gut instinct for most students, I'm going to draw a lone pair. Why do you want to draw a lone pair?
To satisfy the octet.
Satisfy the octet. Before we can deal with satisfying the octet, we have to verify the valence electrons. How many electrons does hydrogen bring into this?
3.
1, but 3 of them, so 3, yes. I was trying to figure out how to answer that. Boron brings in 3, because it's in the third column, which means the total electrons that need to go into my structure is 6. By putting in that lone pair, what have I done? I'm now up to 8. I'm not allowed to do that, because I can only bring in 6, which means there is no lone pair there. And we might be, oh, that's awful, because I don't have an octet. That doesn't matter. Okay? How many of you complained about the octet when I drew out hydrogen?
But that is a full octet for hydrogen. It's a duet.
It's a duet. By that same token, boron's full octet is actually the hextet.
No.
No?
No.
Sextet?
Right.
Okay, there you go.
And what's it?
Socioculturally. Sorry, ignore that. So now what happens? With that missing octet, what would its hybridization be? We have to know about hybridization? Yeah, sp2, which means what's left over? A p orbital. And what could you possibly put into an empty p orbital? 2 electrons from, say, the pi bond. So those electrons can come out and share with the boron. But now I need a leaving group. Is hydrogen a good leaving group? Nope. Does boron have a lone pair of electrons to act as a nucleophile? Nope. So I have tiny leaving group, no nucleophile, which means I have to form this 4-member transition. Those electrons, whoa, that's an eraser. Those electrons immediately come back and attach, and the result being, careful, the addition of the boron and the hydrogen across the double bond. Okay. Boron does its own whole nasty thing that if you want to look up a mechanism on it, it's kind of neat and fascinating and cool. Okay. Ultimately, this is not the final form. It goes through like 6 other things, and it looks ugly and awful, and it fills my entire screen. So I'm not showing it. Okay. So, ta-da, we're there. Is that a stable structure? No. How do we know it's not a stable structure?
Do they add on the same side or not this side?
For this case, what do you think? Should the boron and the hydrogen add to the same side? What happened with our arrows? How many reaction steps did I do? 1. They're adding on the same side. This is officially a syn addition so far. Okay. Again, the mechanism helps us with that. By evaluating these patterns, I can come to that conclusion.
Why did you write B2H there?
That's sometimes what BH3 and THF is shown as. So there are some reagents that, for whatever reason, they like to throw in a bunch of other random crap at you just to confuse you. That's one of them. B2H6 is the same thing as BH3. Are we done?
Oh, is that stable?
Yeah. Well, it's neutral, so that fits the pattern. How many carbon structures have you seen with boron in them? We can even try it this way. How many carbon structures have you seen with boron in them today? Come on, there's at least one. How many carbon structures have you seen today? A lot more than just one. So is boron something that we typically leave in a carbon structure? No, it's pretty reactive. So we have to somehow get rid of it. But in our solution, there is nothing to get rid of it. So how do we get rid of it? That just takes us back to our annoying BH3 stuff to start with.
What about another BH3?
Another BH3 ultimately goes through and does all this. This is that nasty boron stuff. Okay. Preeti, you're the one that brought this up. What happens as you slouch back into your chair? Stop asking me. Stop asking me. Big hint. I added a little 1 there.
That's only the first.
That is only the first step, because there's a second step, and in that second step I add hydroxide and H2O2. Why do I have to do that second step? Because I don't want boron. I need to get rid of it. That's why.
Why would you add it in the first
So is this an example of memorization? You would know that the second step would be with hydroxide?
Depends how you want to look at it, but yes. Okay. My argument would be borderline no. How many times have I seen boron in a structure? No, I've got to do something else. What is that something else I do? Yes, now I have to do memorization. Okay. On a multiple choice test, you'd look at the multiple choice answers and be like, there's no boron, but there is hydroxide. Which means that I've got my hydrogen and OH. This becomes a fun one, potentially within this. Okay. How did the hydroxide replace the boron?
because it took that H.
How did the boron and the hydrogen add to the double bond?
The negative charge?
In a syn addition through the boron's p orbital. How is the boron removed from this carbon? Effectively a syn addition of the peroxide actually across that bond. Meaning the OH directly replaces the boron. Okay. So those of you who were referencing substitution, well, SN2 does backside attack, so it comes in from the backside. Nope. It comes in from the same side. Well, then that can't be SN1 because SN1 is both. This is a simultaneous reaction where it's replaced exactly in the same stereochemical location. Okay. Which is tricky. Okay. You could go through a hand-wavy mechanism that matches what we did with the boron in the first step, but instead of using a carbon alkene, you'd use the peroxide as your reagent. And it does the exact same thing. It replaces it immediately right off the structure. Okay. If you want to see that mechanism after class, I'll show you my hand-wavy mechanism. Okay. This reaction fit which category? Our leaving group was tiny. We're looking at 4-member transition states. Okay. If we look at the beginning to end, I start with an alkene and I add H and OH, and they are added as a syn addition. Okay. The extra kind of layer of crap that we could throw into this, which carbon attacked the boron? Let's go ahead and just do it this way. Which carbon? Yep. Purple carbon, orange carbon.
Well, based on the arrows, the orange carbon.
Attacked the
I'm sorry,
boron?
Sorry, the purple one.
Okay, so based on what I've got drawn, it looks like the purple one. Is there a difference between purple and orange?
Yeah. No.
Why are we saying no? Because they're the same. Yeah, they're the same. Okay. What if I did this?
It would be different.
Now those two double bonds are, those two carbons are different, right?
It would also be asymmetric. No, it was asymmetric.
Yep, it would be asymmetric now. Okay. So which carbon should actually attack the boron? Purple one or orange one? Okay, orange one. What needs to attack the boron? Electrons. Which carbon has more electrons, purple or orange?
Orange.
Orange. So that when I draw the resonance structure for this, you are telling me that this is the correct resonance structure. That'd be less stable than what? Which of those two resonance structures is the more likely one? The bottom one, because tertiary carbocation, which means which carbon attacks the boron? The purple one. Which then means when we continue through this whole reaction to draw out the product, where should the OH be? Same place as what? Where the boron is. So the OH should be connected to the purple. Sorry, what?
This has been discussed anyway.
Yeah. Have we discussed this? Yes, we discussed this in first semester. Theoretically, you all remember this. Earlier today? Oh, I don't think we did that. We did talk about the resonance on those differences. We only brought it in as an evaluation with this reagent. Okay? So the resonance does dictate the end results as well. Okay? So when we look at a reaction, it's not just what's the reagent, oh, it just adds H and OH in a syn addition. But I also have to consider how it added those. Where did the H and the OH go? Which positions? Those positions are very often dictated by looking at the resonance structures. So all of our reactions are pulling all of your knowledge. If at any point you have a weakness, you have to have it all memorized. This is why students tend to freak out in second semester with all the memorization, because you aren't picking up the content on where there's patterns to simplify that memorization process, because you were weak in first semester. Okay? It happens to everybody. What I'm trying to do is set you up with the tools to help you recognize those patterns and potentially catch on to tricks. Make sense? Okay. So there's the general mechanisms for those. We just walked through specific examples for each of those. Okay. If we looked at our cyclotri intermediates, this is showing an extra little complication to be concerned about. What's that extra complication? I don't know, there's lots of stuff up there. Piece it all together, what do you see? Huh? Stereochemistry, how? Nope. In both cases, these are being added on the same side. We're doing a syn addition all the way through this. Well, syn addition for the first step, and then a substitution for the next step. Why are there two directions on this? They're enantiomers. What are enantiomers? Potentially. The two things at the end are potentially enantiomers. How did I get those two things at the end? I added them to different sides of the p orbital. What's the complication with addition reactions? You're using pi electrons. Pi electrons exist where? Above and below the plane of the molecule, which means you have two possible pathways to run the reaction. Nearly all addition reactions result in two products. The relationship between those two products then becomes the next fun thing for you to evaluate. Yay, stereochemistry. Okay? Both of those reactions happen. Very few cases can we actually limit one over the other. Okay? So I believe all of this was actually in the video. We're going to skip over that. Give me some practice. Do you guys want some practice on that?
Yeah.
Draw some products? Draw some products. 4 questions. We turn it into a quiz?
No.
Remember, quizzes are just practice. You're just writing stuff down. No, you don't want to do a quiz. Okay. So, I believe they're all up there. Which one do you want to look at? All doesn't count. Okay, first one. Who got that answer? Did somebody get something else? What's that? You just added the 2 bromines on there. Do we need the stereochemistry? Okay, we do need the stereochemistry because those are chiral atoms. Okay, so we do have to specify the stereochemistry. Okay, if you just drew on the bromines and you tried to draw them trans, I don't want to erase it. If you just drew solid lines with the wedges and the dash, you would at least get partial credit in a show your work type question because you've shown that bromine does add across the double bond. You didn't get the stereochemistry aspect of it, which means you lose points. Okay. There's a very important question. Nobody got anything other than what was shown there? What did you get something else?
No, I got the same color, but I did draw the
Okay. Didn't ask for the I didn't ask for the intermediate, so you didn't need to draw that. I would argue on a test that makes sense to draw the intermediate because that's probably going to help you get that you need those to be anti. Okay, so that is useful and good. You should do so. Why am I asking if anybody got anything else?
Because it's wrong.
Because that answer is wrong. Okay, what's wrong with it? There are two answers.
Oh, so then one's dashed.
Plus the enantiomer because one should be wedged, the other dashed. Yep. Okay. Remember, it's an alkene. You get two additions. You get two products. You have to do it. Okay. The next one down, the lower or the next to the right, the CHCl3. Okay. That one's a bit tricky because we didn't officially talk about that one. Okay, if we go through and look at the reactivity here, we have the alkene, which we should know is not super reactive. We need to find something to react with it. We move to the next one, CHCl3. Anybody know anything about that? Shh. Sodium hydroxide. Does anything know anything about sodium hydroxide? It is a strong base. Would the strong base react with the alkene? What does the alkene act as? A base or a nucleophile. Is a strong base react with a base? Nope. So the sodium hydroxide as a strong base has to react with the CHCl3. Okay? And it removes a hydrogen from that structure, thereby leaving a lone pair of electrons on that carbon with a negative charge. Does that start to look kind of familiar? What can you tell me about chloride? It's a really good leaving group. It's the carbene reaction. Except instead of doing diazomethane with the CH2, you would do it with two chlorines. Okay? We get lots of stereochemistry there. Okay? Did anybody get that answer? Did anybody get anything else? It's a harder one. So, is there an enantiomer for it? Say that again. It's a diastereomer, not an enantiomer. If you write plus enantiomer, you're wrong. Why? The stereochemistry about that position does change. We do get a mirror image there. Wedges become dashes and such. But what happens to the other carbon? It doesn't change, which means the relationship between those two products is diastereomers, not enantiomers. Okay? This is one you can't cheat and just say plus diastereomer on. You'd have to draw the other structure because there's lots of diastereomers. Okay? When we move down to the next one down, which we'll go through a lot faster, the mercury reagent, okay? Big lone pairs forms a cyclic structure known as the mercuronium ion, similar to the bromine. Okay. This one is different from the reaction we showed before because in this case water will attack here. It does not, whoops, come on, it does not attack here. Why? For the same reason with our bromine, the mercury is a really good leaving group. Because it is a good leaving group, we form SN1 type reactions. The water comes in and attacks the most substituted position. Right. So we get the ring opening to our neutral species. That one becomes tricky in and of itself because how many times have we seen mercury in an organic structure? Not. Okay, add to that, how many mercury thermometers have you seen? Why not? Because that's toxic. We don't deal with mercury, we try and get rid of it as fast as possible. This is another one that requires a second reagent to cleave off the mercury. That second reagent, for those of you with good memories, or just me with a good memory, it's okay. Sodium borohydride. Okay. Last one, MCPBA. Okay. All we're going through and doing is making the epoxide. This is a super fun one as far as a mechanism goes because it's just like phenomenally cool. Sorry, not the prettiest. Tons and tons of arrows go into this one, but you end up forming the epoxide. With that, unfortunately, we have to stop. And we can go to office hours if you have questions. If you don't have questions, then you should do some more reading because you should have questions. Okay? So what we're trying to do is get through kind of review stuff on the electrophilic addition. We're going to burn through these at this point. Okay?